The example is basically telling us or asking us to find the tension in each cable at A. So we know there's a vector from here to here, all that has the tension from B to D. We don't know the magnitude, we have to find it. And there's another vector from E to C that is basically vector EC, that is a tension giving us the magnitude of the forces that hold the sign up. There's a force because of the 270-pound sign. And FYI, there's a typo here. They're telling us that the weight of the sign, they're telling us the weight is 270 pounds, but they're using this 270 pounds as pound force, where in reality, for imperial system of units, it is the weight times the gravity. And the gravity in imperial system of units is 32.2 feet per second squared. So there's a typo there, but we're gonna assume the force by the weight of the pound of the sign is 270 pounds force. All right, so let's go ahead and find the reactions at A. So I brought the example to the graph to this page, and what we do is find the reactions. So we already know that there's a force T from B to D, another one from E to C, and the weight. The new concept here is that we're going to have the support at A having us find three forces, X, Y, and Z. So this is we did something like this already. The new concept here is that we have forces holding this sign together at A, B, and C, or basically X, Y, and Z. I apologize. The question is find it with respect to A, so we don't have to find the components of C, because you know there's CX, CY, and Z, AZ, or CZ, which is that way. There's another one for D. So we don't have to find that. We have to find the components around A. So the first thing we have to do is find the lambda vector, which is the unit vector between the distance from B to D and the magnitude. All right, so for that, let's go ahead and put the points A, B, C, D, E, and they have components X, Y, and Z. Okay, so let's start with A. The components of A in X, Y, sorry, the coordinates of A are 0, 0, 0. So that's pretty simple. The coordinates of B are 8 in X, 0 and 0 in Y and Z. C has components 0x, 3y, 2z. Okay, D has components 0, y is 4, and z is negative 8. Okay, and E has components 6 and 0, 0. And there's a point where the weight is, let's call it point xw, which is 4 in X, is 4, 0, 0. And you'll see why we don't care about what's the distance in Y. It's because it's not giving a moment around Y, but we'll talk about that later. So this is 0, 0, zeros. All right, so this is gonna help us find the distance from BD. So R, some space here, R, B, D. So it's basically the head of the vector minus the tail of the vector. So it's going to be equal to D minus B is 0 minus 8, it's minus 8I. D is 4 minus 0 is 4J. D is minus 8 and 0, comma minus 8K, and that is the distance between B and D. One thing that we can do is find lambda, which is equal to RBD divided by the magnitude of RBD, but the magnitude of RBD is negative 8 squared plus 4 squared plus negative 8 squared, and this is equal to 8 squared 64, and 64 and 64 is 120, 128, and 16, 138, 144. So square root of 124 is 12. Therefore, this is the magnitude of BD. Therefore, lambda is, let's do it by components, I, J, K. I don't think I have enough room. Let's do it down here. So lambda BD, equals negative 8 divided by 12 in I, comma 4 divided by 12 in J, comma negative 8 divided by 12 K equals, so this is an important value here, is 4, 6, 2, 3, negative 2/3 in I, 1, 3, 1/3 J, negative 4, so this is 4, 6, 2, 3, negative 2/3. And there is lambda right there. So this has to be less than 1, which it is less than 1. The denominator is greater than the numerator. So the force, the magnitude of the force TBD from B to D is equal to, this is the vector, is equal to the magnitude, which this is what we have to find, times, well, we have to find both, right? This is the magnitude and this is the component. Negative 2/3 in I, 1/3 in J, negative 2/3 in K. All right, we already found one. Now we have to find the other one from E to C. So let's go ahead and while I'm doing this, you can compare right here. So let's compare negative 2/3, 1/3, negative, yeah. So far we're good. So this is the part that usually we get confused at. So let's be very careful. So R between E and C is equal to, so let's go up here, 6 minus 0, because it's C minus E. C minus E. Oh, so it's 0 minus 6. Yeah, because the end of the vector is at C. It's the ending point minus the beginning point. No, I said that wrong. Is the head, which is the where the vector ends minus the starting point. So it's C minus E. 0 minus, well, that's pretty convenient, is 0 minus 6, which is minus 6, comma, then 3 minus 0, 3j, comma, and 2 minus 0. 2 minus 0 is 2. All right. So they get negative 6, 3, 2. Okay, so far so good. We're doing perfect. Now the magnitude of that vector is equal to square root of negative 6 squared plus 3 squared plus 2 squared, which is equal to 36 plus 9 plus 4, which is equal to 36 and 4 is 40 and 9 is 49, square root of 49. So magnitude of REC equals to square root of 49, which is 7. This is an important aspect or value. Okay, so that is the magnitude of these meters, right? This is meters. 7 meters is the length of that cable. Is the length, not the force, the length. This force is 7 meters. I mean, the length from E to C is 7 meters. The length from B to D is 12 meters. Therefore, lambda EC equals the vector EC divided by the magnitude of EC, which is equal to negative 6 divided by 7, that is less than 1. 3 divided by 7, less than 1, we're good. 2 divided by 7, which is less than 1. Therefore, lambda EC is equal to, we'll just leave it like that. And the force, vectorial force of E to C is equal to the magnitude, which we have to find to C, E to C, times negative 6 over 7 in I, 3 over 7 in J, 2 over 7 in K. All right, so we're doing perfectly fine so far. Then we have the system of equations that let us see right here. So the system of equations that we have is summation of forces in X equals 0. This is the new concept right here. So we have a force in AX positive. I'm just going to put all of them positive. So there's a component right here, a component right there, and a component right there. Okay, so let's find those forces right there. So in X we have Bx, or basically T B to Ex, which we should have it around here. So plus, where is my vector that I just found? Here, negative T 2/3 of T to B. So actually negative 2/3 times the force from B to D. Which one is the next one? In A is also negative, which the math gave us the negative sign. That's always gonna work out for us much better. And this is negative 6 over 7 times TEC equals 0. And let's see, they should have their equation set up too. So A minus 2/3 minus, yep, so far we're good. Let's set up the second equation. Summation in Y equals 0. So we also have a force in Y, right, which is this force right here, AY. And then we have another one from T B to D, which is 1/3. So that's positive T B D divided by 3. And then positive T e to c times 3 divided by 7. Let's check with what they got. 1/3, 3/7. Yep. And then we're not done yet because we have a force in y that is given by the weight of the sign. So this is the type what I'm talking about. They're telling us that the weight is 270 pounds, which is correct, but the force, because of the weight, is the weight times the gravity. Well, actually, no, that is correct. They tell us the weight, not the mass. If they gave us the mass, then it would be like this. Okay, no, they're actually correct. So I jumped the gun. This is negative 270 pounds in J. Right. So in summation of forces in Y, we have to account for that. Negative 27, or actually equal to 270 pounds in J. All right. We should have one last equation. Z. Summation of forces in Z equals 0. Obviously, we have a force in Z. Let's see if it's positive or negative. Negative 2/3 of the tension from B to D. And then positive 2/7 T e to C, and this is equal to 0. All right, let's just double check. AZ minus 2/3 T to B, 2/3, yeah, B to D, and positive 2/7, this and this is correct. Yeah. Okay, so please notice that we have three equations. 1, 2, 3, and we have 1, 2, 3, 4, 5 unknowns. We have three equations and 5 unknowns. That means that we need at least 2 more equations. Yeah, because if we have we need 5 equations for 5 unknowns. If we have 6, 7, 8 equations, then that's redundant. We just choose one from those to have 5 equations, 5 unknowns. And the way to get those equations is from the summation of moments. So this is the other concept that we're learning today with this example. The summation of moments around A is equal to 0. And we should have a summation of moment when AX, summation of moment because of AY, or around, well, let me say that, yeah, the point A around axis, from axis Y, and summation of moments at point A with contribution axis Z. All these things are equal to 0. So in math, you would say that that moment and that moment and that moment, all of those are equal to 0. So let's set up the equations. So summation of moment A with forces in X is equal to, this one is going to be pretty easy, because if you notice, the forces in X have no perpendicular distance with the point A. Notice this one W doesn't have a component in X, E does not have a perpendicular distance with A, so they're applied on the same axis X. Therefore, this one is equal to 0. Hence, that equation is not going to help. Let's do another one. Summation of moments around axis Y is equal to 0. And which one is that? So axis Y, I'm sorry, is any moment that is counterclockwise or clockwise around Y. What force is causing to be rotating around Y? So you assume the force is too big and it will make it rotate around like a toy. Make it rotate around that axis. And the forces that will make it rotate around that axis are the ones in Z, parallel to Z. So the one T, B, from B to D for component K, and the same for E to C component K. So let's look at those. There's only 2. So it is going to be negative 2/3 BD. So negative 2/3 TBD times the distance, which is 6 plus 2, 8 feet. All right, and then the other one, which is from E to C, which is this one, and K is 2/7. And the distance is 6 feet. Okay, so now we have equation number 4. All right, and then equation number 5 is summation of moments around Z equals 0, and which forces will make it rotate around Z? Well, the weight is going to make it rotate around Z. And remember, counterclockwise is positive, and clockwise is negative. So anything that goes, actually, that is negative because it's clockwise. So this is clockwise, that is negative. Counterclockwise is positive. The weight is going to make it rotate clockwise, so that's negative, but the tensions are going to be applying a positive moment because they're going to go counterclockwise. So let's do the positive first, and then we do the negative. So we're going to have plus, what is going on over here? Oh, yep, this is the wrong one. So plus minus equal to 0. All right, so plus, the first one is the one from B to D, and K, sorry, in Y, yeah, in Y, and that is 3/7. Nope, is B to D, is 1/3. Yeah, because it's the one in Y. So the one in Y for B to D is 1/3. So 1/3 of TB to D times, and the distance is the same as before. From A to B, we have 8 feet. 8 feet. So this is pounds, this is feet. The moment is pound feet. All right. Now we have the contribution of E to C, which is also positive. So 3/7 tension E to C times the distance, which is 6. Yep. Minus the distance is 4 and the force is 2,700. Minus the force, which is 270 times the distance, which is 4 feet. Okay, so actually we can compute that. So let's go ahead and let's do 270 times 4 is 1080. This number is 1080 feet per pounds per feet. Okay, equal to 0. Perfect. So let's check our equations. We have negative BC is negative, well, 171.4. We have 2/3 times 8 is 16/3. Let me see. Did we do something wrong? Let's see, in J, what is going on here? In J, we have 533 times BT, and that is, what are we having here? Negative 2/3 times 8. That is 16 divided by 3. Well, what is 16 divided by 3? 533, okay, and they have 533 positive. We have negative. Why do we have negative and they have positive? Because we take the force negative 2/3, and that negative 2/3 in I, negative, okay, I have a typo here. So if you take the force with the direction given, okay, so negative 2/3, so I have negative force in X, meaning that, well, sorry, first of all, next we don't have any values. Is positive 1/3, yeah, 1/3, I think I did something wrong here. This is 1/3 and negative 2/3. Oh, I'm looking at the wrong thing. Am I? Negative 2/3 times 8. Negative 2/3, this is a negative force, and they are getting a positive force. And it's because the negative force in Y is applying a positive moment. Oh, yep, that is why. So that is why, that is my mistake. So even though this is a negative force, is applying a positive moment. So at that point, you don't bring the force and the sign. At that point, you bring the moment sign. So this, wait a second, let me confirm, because that clockwise is indeed negative. Okay, so we have negative 8 and they have positive 2/7. They have it positive, but we have it negative. How come? If our systems of equations are the same. Let me double check one thing. J is positive 1/3 TB to D, and 3/7 equals to 270. Yes, that's what we have. So they're saying that even though the force is positive, the forces are positive, and these forces are positive, the positive force is causing a negative moment. Okay, let's see. So both forces are positive. Yeah, TBD and TEC are positive. And then the distances are, or E to B in Y is 1/3. Okay, so is 1/3, where's my force at? Yeah, 1/3. Wait, but why is my force not giving me? Let me see. Around Y. So around Y is the force in K. The moment around Y is the force in K. What is the force in K for TB to D? TB to D that has a negative force, meaning that a negative force goes like that. And oh, yes, sir, that is true. Okay, they are correct. So if you place the forces the right way, so we're gonna have to bring this down here. Okay, so all right, let's see what we have. All right, so because of the forces that, let's see, E to C is telling us that in X is a negative force in X, in Y is positive, and in K is positive. Okay, and B to D, this is the part that we have to be careful, is negative in X. Yeah, that makes sense. It's going back there. Is the blue equation is positive in J. Yeah, that makes sense. And this is the part that we need to be careful. Is negative in K. Okay, is negative in K. All right, so let's see the point B. So if we take that force, which is negative B to D, that is applying a counterclockwise moment. So it's positive. Yep, that is correct. So we have a positive and bring the force over here. And the force, the positive Z component is 2/3 K of T B to D. Okay, so we bring it here. All right, and times 8. So 2/3, let me use this calculator here. 2/3 times 8 equals 533 and a positive moment. And then the next one is E and E to C. And this force, even though it's positive, is making the sign rotate in a negative moment. Yeah, and we said that we're going to consider the moments counterclockwise positive. Therefore, that force, even though it's positive, is going to make it rotate clockwise in a negative moment. Therefore, that is true. This is a negative force. And that is what they have. They have a positive and a negative. Oh man, okay, let's check our next equation. Around Z is forces in Y, but we said that both of our forces are positive, therefore both are counterclockwise and both should be positive. Okay, and let's see what they get. Two positive forces, yeah, two positive forces equals to the moment of the weight times 4, and 266. We have to make sure we have the same numbers, otherwise those 5 equations are going to give us different numbers. All right, let's go to Wolfram Alpha 1. So 8/3, 8 divided by 3 is 2.66. What is their computation? 2.66. Okay, good. And then for E to C is 18 divided by 7. So 3 times 6 is 18 divided by 7. 18 divided by 7 is 2.571. 2.571. And that's what we get. Okay, cool. So good thing we're confirming, otherwise we would have made a mistake. So yeah, and remember that in this case is because this is the force magnitude. This is the magnitude of the force. So you don't bring the sign with it, and you apply the sign given the moment around the axis. So be careful there with that setting up the moments.